we were talking about, before we left last class, electron configurations for given elements. So, for example, if I'm thinking about an atom, let's talk about silicon, for example. All right, if I'm going to look at silicon here, and I want to write its electron configuration. All right, how do we write the electron configuration for silicon? Well, let me see if I can. All right, so we're going to write the electron configuration for silicon. Now, what is this electron configuration? What is this for? What's it's useful for? Make sure to put this a little bit better. So, what the electron configuration does is it tells us where all the electrons are kind of residing, or you could say where they're at on this given atom. Okay, and what that helps us with is hopefully helps us identify the energy of the electrons and possibly the relative stability gained by the atom if it were to lose or gain electrons. Okay, so let's write the electron configuration first, and then we'll have a talk about how our orbital diagram kind of leads us to understand how the given electron configuration gives us information about the stability of the atom or its electrons. Okay, so here's how we write the electron configuration for silicon. We're writing all of its electrons, and it has a total of 14 there. All right, 14 electrons. And those 14 electrons need to be identified in this electron configuration. And what we do is we write, of the 14 electrons, the first electrons have an N value of 1. They have an L value of, let's see if you can remember. If I say these are S electrons, what is the L value, Aisha?
0.
0. Very good. Let's do a little quick review up here. For our L equals 0, 1, 2, or 3, we have letters, shorthand, S, P, D, and F, to refer to those L values. So very good. Now, I don't know if I talked to you guys about this last class, but when I ask a question, I'm going to look for the person who's on that list there, the next person on the list. So I just asked Aisha a question, so the next question I'm expecting Alyssa to answer that question. So you can be ready to answer the question, and after Alyssa it would be Anastasia, and moving down, so forth. Okay, so you can be ready to answer the question if you're next in line for answering the questions. That'll decrease any time loss when the question is asked. All right, and if you don't know, just say, wow, you know, I don't know. And that's a great answer, right? There's nothing wrong with that answer. We know that that's how you're supposed to answer when you're in your small groups anyways. And you can answer, I'm not sure, I'm not positive, but I think it is this if you want to. Okay, so 1s, and then we put a 2 up here to indicate that there are 2 electrons that are in that 1s subshell. All right, and these are electrons that have similar electron configurations to hydrogen and helium. Now the 1 corresponds to, let me get a periodic table here. So I can mark up this periodic table. The 1 corresponds, N equals 1, to the first row here, right? 2s corresponds to this, the S block. All right, and you know, helium is over here, but it really could be considered over here in the S block for these types of electron configurations. So after we do 1s2, that's 2 electrons, hydrogen and helium. The next 2 electrons are lithium and beryllium. This is N equals 2, the second row there, and 2s, meaning the s block, right? And then there's 2 electrons, lithium and beryllium. So I say 2s2. So I can follow along in the periodic table to know where the electrons, how the atom goes filling and where the next electrons will be. So 1s, 2s, and then we have to go over to here. And this is, what is the name of this block, Alyssa? Do you remember? What's that?
P.
Yeah, that's right. This is the P block. The P block, all right? So this second row, P block, is going to go to P, and the number of electrons, 1, 2, 3, 4, 5, 6, and we need to fill all the way up because we got to get all the way to silicon. So we say 2p6, 2p6 electrons. After 6, 2p6, that would end us at neon. Next we go down to here. This is n equals 3. Right here, it's the s block. So we have 3s2. And then we go over to here. What would the last, Anastasia, what would the last little units be there? How do we finish up this electron configuration?
I'm not sure.
Okay. Well, it's on the third row, so it would be 3, right? And it's in which block over here, Anastasia? This is the P block.
P block.
Very good, the P block. And so it's going to be 3p. And if we want to get to silicon, how many electrons in the 3p do we need to get?
2.
2. 3p2. Very good. Excellent. So there it is. That is the electron configuration for silica. Okay? Now, let me show you really quick how we write the electron, the abbreviated electron configuration for silica. What we do is we find our location for our element, silica, right? Find our location here. And we go back to the first noble gas, which is neon. So the noble gas abbreviated form would be neon, which essentially is saying we have a neon core, which is 1s2, 2s2, 2p6, and then I pick up from there with this stuff, 3s2, 3p2. All right? So this is saying the same thing. This is basically saying I have a neon core with 2 electrons in the 3s and 2 electrons in a 3p. Okay? So these again are called electron configurations. All right, and what is why is this helpful? Well, it's helpful. It can be helpful for a variety of reasons, but we have to be sure that we recognize that this energy diagram, or orbital diagram, where we have our 1s, 2s, 2p, 3s, 3p, we have to have this in mind when we're thinking about the silicon atom. All right, the 1s2 shows that there's 2 electrons here, 2s2, 2 electrons there, 2p6, 6 electrons there, 3s2, and then 3p has 1, 2 electrons. All right, so now when we can keep this in mind, if we can keep this in mind, we can answer and understand a couple of questions, a handful of questions. One is, we can see that if this element wants to fill that outer subshell, it's going to need 1, 2, 3, 4 electrons. Okay? 4 electrons. And you already knew that because of its location on the periodic table, right? Silica 1, 2, 3, 4. All right? So it's not like it's amazing news to us, but it can also teach us about what happens, other ways of finding stability for the atom. Because again, why does it want to get 4 electrons? Because it's going to attain a noble gas electron configuration, which will bring it stability. But there's other ways that elements can gain stability, and these are the ways. An element can gain stability by completely filling this subshell, and that's what we just said here, putting 4 more electrons on to have an argon configuration. Or it can find stability simply by half filling a subshell. So if this, and you can kind of look at this diagram and say, yeah, it feels kind of funny because we just need 1 more electron there to find kind of balance. And if you put an electron in there, that electron will provide a little bit of stability to silicon. So another way to find stability is to completely empty an outer subshell, or a subshell. So if we remove 2 electrons from silicon, we can find stability as well. So silicon can find stability 3 ways. The most stability it'll find is if it can gain 1, 2, 3, 4 electrons and become an electron like a noble gas. But that's a lot of electrons. That's going to kind of a tall order for that. The second best way that it can find stability is to fill half fill its subshell, which will be gaining 1 electron. And another way it can find stability is by losing those 2 electrons, so it has an empty subshell. All right? So if we go back just briefly and look at sodium and think about our old understanding of sodium, right? Sodium likes to perform chemistry, and this is going to be a question for you, Brielle. Sodium likes to perform chemistry by doing what? What do we know about sodium? When it's in chemical reactions, what does it like to do, Brielle?
Become closer to the noble gas.
That's right. How does it do that? How does it?
It loses an electron.
That's right. We know that elements in this first group lose an electron. Okay? And they become neon. And basically, we've said, because we want to have noble gas electron configurations. Sodium starts with 11, wants to have 10. Now we have kind of a way to visualize that on a orbital diagram. If I draw an electron orbital diagram for sodium, 1s2, 2s2, 2p6, 1, 2, 3, 4, 5, 6. And then what's next for sodium if I want to finish up sodium? 1s2, 2s2, 2p6. If I stop right here, where am I at? Camilla. If I stop right here, where am I at? One S2, 2s2, 2p6. This is at neon. Are you there, Camilla? Camilla Clark?
Yes, I'm sorry. I don't know.
Okay, all right. If I stop right now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So I can always just count the number of electrons to find out where I'm at. I'm at neon. If I want to get to sodium, how many more electrons do I have to add, Camilla?
You're at neon?
I'm at neon, that's right.
Just one?
Just 1 more electron. And where is that going to be? What subshell is that going to go in?
S.
And that's right, 3s. And then I have 1 electron. Okay? So, ways to find stability. What were the 3 ways to find stability? Camille, Dinsdale? What were the 3 ways to find stability that we said? We could either do what?
I don't know. My brain's going directly to like n-1 and all that stuff we learned the other day.
Okay. So the ways that we can find stability, we said, is to obtain a noble gas electron configuration which would be lose that electron, or maybe gain 1 electron and have a half-filled subshell, right? But because it's not too bad to just lose or gain 1 electron, it's going to lose that electron to form a noble gas electron configuration. So if I've changed this to a positive charge, what does that mean I've done to the number of electrons?
Lost 1 electron.
I've lost an electron. That's right. So this electron will be gone now. And my electron configuration for the sodium ion is 1s2, 2s2, 2p6. 1s2, 2s2, 3p6. That's the electron configuration for the sodium ion.
How did you get 3p6? Like, why is it 6?
Sorry, not 3p, is it? It's 2p. 2p6, right? 1, 2, 3, 4, 5, 6. Is that what you meant?
Oh, I get it. Thank you.
Okay, very good. So, when we look at an electron configuration, we have to kind of have our orbital diagram in mind and look at those. And we're always going to be looking at these last electrons, right? Because it's all about finishing up that last subshell or emptying that last subshell to find something that's more stable. And we can stabilize it by getting a noble gas electron configuration, or we can stabilize it by getting a half-filled subshell. That's a little bit of stability, or by emptying a subshell. Okay, so let's also introduce to you, I'm sure you guys have heard this term before, but if I take an element like, let's go calcium here, calcium, and I write the electron configuration for calcium. All right. So I want to write the electron configuration for calcium. I want you guys to go and do this, okay? So we're going to create some breakout rooms here. If you guys can go and write the electron configuration for calcium, all right, the electron configuration for calcium. I'm going to give you just a little bit over a minute, and then I'm going to bring you back in. Okay, so please discuss, and then we'll get back together and see what you guys got. All right, we're looking for the electron configuration for calcium. Okay, go.
Hello.
Is that Kylie?
Yeah.
Fala, are you there?
Yeah.
Oh, great. What do you guys think? What's the electron configuration for calcium?
I'm pulling out my periodic table right now.
Hmm?
I'm pulling out my periodic table.
Good.
For calcium, is it like
It's always the same to start off, right?
1s? Oh yeah.
Good.
Is
What
it
is it?
1s2?
Yeah, 1s2.
2s2.
Mm-hmm.
2p6.
Yeah.
I can't see but 2p6 and 3s2.
Yeah, 3s2. And that gets us to where? If we stop right there, where would we be?
Wait, what are we looking for? Calcium?
Yeah, we're going for calcium. We're at 3s2 now.
2.
That's magnesium, right? 3,
Oh,
third row, S, first S block there, 2, second electron in magnesium. All right, so what's after 3s2?
3p.
3p 6, right?
Yeah, 3p6.
Kylie, are you following?
Wait, after 3s2 is 3p6?
Yeah, because you go from sodium, magnesium, that's 3s2, and then you go across over to aluminum. That's 3p. That's the third row, p block, aluminum to argon. That's 6 electrons. Does that make sense?
Yeah.
Okay, then what's last?
Is it D or do we go to the S?
We go to potassium and calcium, right? So it's 4.
Oh, okay. 4s2.
4s2. Very good. And that's where we would end if we wanted to have calcium. Does that
That
make
would
sense?
be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2.
That's right. Very good, Kylie. Okay, we're going to end the breakout rooms and we'll get back together now, okay?
Okay.
All right, let's all get back together now. We're looking for the electron configuration for calcium, right? Electron configuration for calcium. Let's see. Camille, Chance. Did you get it, Chance? Did your group get it? What's the electron configuration for calcium?
We did the abbreviated version.
Okay, the abbreviated version.
Argon in brackets. And then 4s2.
So that's a lot easier, right?
Yeah.
Argon, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, right? And then 4s2. So these are the two electron configurations for calcium. This is the abbreviated version because this is basically right there the argon core. All right? Very good. Excellent.
The longer version.
How do you know the, where you say 2p, is this, how do you know 1s2 and 2s2 and 2p6?
How do we know these? I mean, how do we know that that's where we start?
Yeah, how does it switch from S to P, then back to S, and then that
Okay.
stuff?
So look at this periodic table. Can you see that really well there?
Yeah.
All right. So the periodic table tells us what needs to occur. Because if we're going to calcium, the 20th electron, we have to start with 1 through 19 first and work our way down to the 20th. And the first electron, actually the first two, right, are 1, n value 1. So n value corresponds to the row, right? And because there's 2 electrons in this S subshell, now we talked about how heliums could be over here when we're talking about electron configurations, because the first 2 electrons are in a S orbital. So the first 2, hydrogen and helium, are in 1s2. All right, so I'm going to try to write this down here in the little corner really small. One s2. So this is the electron configuration for calcium. So I'm going from hydrogen to helium. That's all, both in the first row, and they're both in S. Now this is really over in P, but for electron configurations, it's an exception. It should kind of be here. After I'm done with the first 2 electrons, I go to lithium and beryllium. This is the second row, so n equals 2. N equals 2. And because n equals 2, and there's in the S block, then I go to S, n equals 2. That's what the value here is, the n value. The S is the L value, which corresponds to 0. And then the 2 up here tells me 2 electrons. So I have 1s2, 2s2. If I want to keep adding electrons to this atom, I have to go over here now to 5 through 10. Well, this is n equals 2, second row still, but this is the p block now. Over here is our p block. So it's 2, n equals second row, n equals 2, p, L equals 1, p, and there's 6 of them. So I have to do 2p6. After neon, I would go into sodium and magnesium. This is the third row. That's n value is 3. It's the s block, right? So that tells me that my L value is 0. There's 2 electrons. So it's sodium and magnesium are 3s1 and 3s2. So there's 2 in the 3s. Next, third row, p block, 3p. I want to fill all the way to argon because I need to get to calcium eventually. So it's 3p6. After that, next row, 4, s block, 4s, and to get to calcium, there's 2 electrons. Did that make sense? Who was that asked that question?
That was me, and that makes a lot more sense. Thank you.
Excellent. Okay, so the electron configuration shows us, and we'll do, again, the noble gas electron configuration right below here. Argon is our core, and then 4s2. Now, there's a couple of things that these electron configurations show us. One thing is it shows us what we call our valence electrons, Now, valence electrons are electrons that the atom is kind of willing to do chemistry with, okay? And so for this atom, calcium, the electrons with the highest n value, right? So the n value for these electrons is 1. The n value here is 2, right? N value for these 8 electrons is 3. But the n value for these ones is 4. The electrons with the highest n value are called valence electrons. So calcium has 2 valence, meaning those are the electrons that calcium is willing to wheel and deal with, to do some chemistry with, right? There's 2 valence electrons for calcium. Okay, now let's do the electron configuration for iron. All right, now we're going to do this one together, and we're going to do the noble gas electron configuration, the abbreviated form, just to kind of speed things up for ourselves. But for iron, right? Here we have iron. We have to go back, if we're doing the noble gas configuration, to the first noble gas, and that's argon. So iron is an atom with an argon core, and then, where are we at? Chloe, what's next on iron's electron configuration? What goes next here after the argon core, Chloe?
4s2.
Very good. Argon, and then we're here on the n equals 4, 4s2. So now we're at calcium. And now we have to add 1, 2, 3, 4, 5, 6 electrons to get to iron. Does anybody remember? Let's see. Chloe, Daisy, what is this block called? The transition metal block. In terms of its...
Isn't it the D block?
That's right. This is the D block. So these electrons are going to be going into the D orbitals. All right, we need 6. We're going to put the 6 up there. Now the only thing that I haven't written is the n value. And this is the first time we've introduced it, so pay close attention. When you go into the D block, we would expect we're on the 1, 2, 3, 4th row, so we might expect that the n value for these elements is 4, but when you're in the D block, the n value is always suppressed by 1. So whatever row you're on, it's n minus 1. So these are not 4d electrons, these are 3d electrons. Okay, so we go 4s2 with potassium and calcium, and then we go 3 D, 1, 2, 3, 4, 5, 6, to give us an electron configuration for iron. All right? And then we have the question, which is a reasonable question on an exam. How many valence electrons does iron have? How many valence electrons does iron have? You want to take a stab at this, Ephraim? What do you think? How many electrons, valence electrons, does iron have?
4, but I'm not sure.
Okay. Well, remember, valence electrons are defined as electrons that have the highest N value. Highest N value. Now we can think about argon here. We can go back to argon, back up here to remember. But this is what the core of argon looks like. 1s2, 2s2, 2p6, 3s2, 3p6. So these all have N values of 1, 2, or 3. But these two electrons have the highest N value. And so how many valence electrons does iron have? The answer is going to be 2 valence electrons, because there's 2 that have 4, which is the highest N value for all the electrons here. Now you might say, well, what about those? We call those pseudovalence. And there are 6, in this case, 6 pseudovalence electrons. All right? Now, I've never really seen questions about pseudovalence electrons. It's usually just about valence electrons. And valence electrons are, again, identified because they have the highest N value. But pseudovalence electrons are important for understanding different properties of elements. And specifically, what we find ourselves in is a situation where we can now begin to understand why transition metals form the charges that they do. Okay, so let's look at let's look at iron's orbital diagram. Okay, let's draw an orbital diagram for iron and try to understand what it's doing when it does chemistry. Okay, so orbital diagram, here's the energy. We're drawing an orbital diagram for iron. I'm going to take a shortcut. We know that. We'll bring this up again. The argon core is 1s2, 2s2, 2p6, 3s2, 3p6. Well, maybe I better not take a shortcut on the first one. Here we go. We want no shortcuts. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What's after 4s2 in our iron electron configuration? After 4s2 was 3d6. 3d looks like this. 1, 2, 3, 4, 5. 3d. All right. All of these are full. Remember, when we fill subshells like this, we have to fill each orbital gets 1 electron, and then we fill them up. 4s2, those are our valence electrons, and then 6 electrons in the 3d, right? All right, so this is the electron configuration. Argon, 4s2, 3, 4s2, 3d6. All right, so 4s2, 3d6. It has to feel like this. 1, 2, 3, 4, 5. Every orbital has to get 1 before we pair up, and then a 6 gets paired up there. All right, so.
I have a question.
Yeah.
Why are there 5 lines in the D category?
Well, those 5 lines correspond to, do you remember what the L value is for D? L can be 0, 1, 2, 3. What does L equal when we're talking about D? Let's see.
Clue.
2, that's right. This was SPD. So we're talking about L equals 2. That means if L equals 2, what are my possible M sub L values? If L equals 2, M sub L can be?
Anything greater than 2?
No, remember it ranges from negative L all the way up to positive L.
Oh, so negative 2 to 2.
Negative 2, that's right. Negative 1, 0, positive 1, and positive 2. Those are our possible M sub L values. And because I have this many different possibilities, 1, 2, 3, 4, 5, I have to have 5 orbitals in that subshell. That's what that M sub L value tells us. The number of M sub L values tells us how many orbitals there are in that subshell.
Thank you, that makes sense.
Okay. So now I have...
I have a quick question, sorry.
Go ahead.
I kind of looked at it as like, with the line in the graph, since like the S block has 2 like different, like lithium and beryllium is like 2, then it's just like each line represents 2 of them. And so like there's 10 in the D block, and then you just divide that by 2, and that's 5.
That's great. Yeah, that's right.
That okay to look at it like that?
That's, I mean, it's the same answer, really, right? Because what we're seeing here is that our periodic table is basically displaying this information. And we have to be able to kind of perceive it, but that's right. You can count across a subshell, like the D subshell here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can know that each orbital has 2 electrons, therefore there's going to be 5 subshells, or 5 orbitals in that subshell. Same thing across here, 6 electrons across the P subshell, therefore that's going to be 3 orbitals across that subshell. How many do you think are going to be across here in our F block? Now this periodic table is a little bit confusing because you have lanthanum and actinide, which really belong in this location right there. But then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So with 14, how many 14 across here, how many subshell, or how many orbitals in that subshell are there going to be?
It's going to be 7.
7, that's right. And that corresponds with, if L were to equal 3, then my possible M sub L values would be negative 3, whoops, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. Okay?
I had a question.
Yeah.
So I kind of want to go back to the valence electrons really quickly. And
Yeah.
how to find, let's say, the valence electron. I don't know.
All right. So what we're looking for in an electron configuration. So let me write quickly the electron configuration for titanium. Titanium. Here's the electron configuration for titanium. I'm going to go all the way through the beginning so we can see it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? Now I'm at calcium. I got to go to titanium, 3d2. All right? So if you can write the electron configuration, then you can pick out the valence electrons. So the question is, how many valence electrons? By looking for the highest n value, who has the highest n value here? What's the n value for these electrons, Chance? Say it again.
Is that 2?
2, that's right. The n value for these electrons, that is the n value, is 2. Who has the highest n value?
4s2.
That's right. So now, how many of those highest n value electrons are there? That's 2. So this has 2 valence electrons for titanium. How many pseudo-valence electrons are there? That's these ones. It's the ones that are outside of the noble gas core. What is the noble gas core for titanium? Chance, what's the noble gas core for titanium?
That argon?
Yeah, that's right. That's argon. That's the noble gas core. Here's the junk outside. Whoops. 4s2, 3d2, right? Here's the stuff outside. These ones are valence because they have the highest n value. And these ones are our, what do we call those?
valence electrons.
Pseudo-valence electrons. Very good.
So there'd be 2 of them.
2 pseudo-valence, same as number as valence electrons.
Okay, thank you. That helps.
Okay, so let's go back to our iron now. We're looking for valence electrons, and we're looking for our pseudo-valence electrons, and we're trying to understand why iron does the chemistry that it does. All right. Now, we know from our experience with iron, we've done lots of problems, we've talked about it in the past. We know that there's 2 things it likes to do. It forms ionic compounds, right? That's what it does. And when it forms them, what are the kinds of ionic compounds it forms, Jacob? What are its ions when it forms ionic compounds, Jacob? What are the possible ions that iron forms, Jacob? Are you there? How about Jajar? Jajar, what are the possible ions that iron forms? Or I guess Jajar doesn't have a microphone. Jenna, what are the possible ions that iron forms? Jenna?
Did you say possible? What was the question?
Possible ions. Remember, iron forms a plus what?
A +2.
It either forms a +2 or it forms a... Anybody remember?
Is it +3?
Yeah. It either forms a +2 or +3. Now, that wasn't something we needed to have in our memory at this point in the game. And we really, hopefully, never have to anymore either, because... Am I still there? Can you hear me?
Yes.
So for some reason my video paused. Oh, are we working now? Okay, we're okay. So now we can use our orbital diagrams to kind of identify why iron wants to form a +2 and why it's willing to form a +3. Okay? So if we look at our orbital, our electron configuration, we can say it wants to form a +2 because in forming a +2, it's getting rid of its valence electrons. All right? So if we were to draw this electron configuration, let me redraw the electron configuration for iron +2. Now I'm definitely going to use a shortcut. There's my energy. I'm going to draw the electron configuration for the iron +2 ion. I'm just going to say argon core, 4s2, or 4s, and then our 3d, right? Because I don't have time in my life to redraw it over and over and over. 4s2, the electron configuration for the 4s2 ion, or sorry, not 4s2, but the iron 2+ ion, is argon with 3d6, right? What happened to the 4s2 electrons? Where did the 4s2 electrons go? Is it Jenna's turn? No, Jenna just answered. Kylie Barnes? Where did the 4s2 electrons go?
I'm not sure, but did they cancel out?
We lost them because we now have a +2 charge, right?
Yeah.
So we went from the electron configuration for iron is argon core, 4s2, 3d6, whoops, 3d6. We went from this to an iron +2 by doing what? What did we do, Kylie?
You lost 2 electrons?
That's right. I lost those 2 electrons. So we no longer put little indicators of electrons there. I still have to show my 6d electrons though, right? 1, 2, 3, 4, 5, and there's my 6. All right? So this is the iron +2, argon core, 3d6 electrons. Very good. Now, what would happen? What would have to happen if to my electron configuration if I'm going to go from iron +2 to an iron +3? Here's the energy again. Argon core, 4s2. What's going to be the difference here? with the iron plus 3, Koa? Are you there, Koa?
Yeah, I would have to lose another electron. And I actually had a question about that. Is it, so it's plus 3 because you said one of the 3 ways that it becomes more stable is if it goes to half of its electron shell or something along those lines. And so by doing the plus 3 instead of the plus 2, it goes to half. Is that essentially what you're saying?
That's right. Very good. So we have 3s2, or sorry, iron plus 3 would result in, again, the argon core. And what would I have left here if I now lost 3 electrons? 3d what, Koa?
3d5.
3d5. Very good. 1, 2, 3, 4, 5. Doesn't that just feel good when you see that compared to this, right? It just looks so much prettier, right, without that extra electron there. And so iron finds stability 2 ways. It finds stability by losing the 4s2 electrons. Let me write up here the electron configuration for the iron atom, again, just to remind us. Argon core, 4s2, 3d6. All right? So we find stability by losing those 2 valence electrons, iron plus 2, and we can find further stability, or an additional amount of stability, by losing 1 more electron to leave behind a completely half-filled subshell. All right, do you guys see that? Are there any questions about that?
I have a question.
Yeah.
So why is on the D block, so there's 10 elements, and so then there's 5 for 3D, but why is there 6 electrons to begin with?
Well, it's just for iron, right? Iron here, we had to have 6 electrons to go 1, 2, 3, 4, 5, 6.
Okay, that makes sense.
Yeah. Now, there's a lot of different properties that occur because of the number of what we call unpaired electrons. And one of the properties associated with unpaired electrons is, remember how I said that these represented the spin of the atoms, electrons, and that spin could be influenced by a magnetic field. Well, this number of unpaired electrons represents or relates to what we call magnetic susceptibility. So people or questions like to ask the number of unpaired electrons in a given atom, because that tells us information about magnetism, magnetic susceptibility of an element. Okay? So, if you look at the iron atom by itself, this one right here, this is the last question before we leave. If we look at the iron atom by itself, how many unpaired electrons are in this iron atom? Let's see. Kylie Johnson, are you there? Do you have any ideas? How many unpaired electrons are in an iron atom?
I have no idea.
All right, well, let's go over to this electron configuration. Let's make it an iron really quick. Let me add in the 4s2 there. I can look and see that these electrons are paired, these electrons are paired, but I have 1, 2, 3, 4 electrons that are unpaired. Can you see that, Kylie? And if I make it an iron plus 3 ion, then I actually have 1, 2, 3, 4, 5 electrons that are unpaired. So that's a common question as well. How many unpaired electrons are there in a given atom? And the electron configuration, along with the orbital diagram, will tell us how many unpaired electrons there are. All right, excellent. I'm working on a chapter 8, 1 through 8 exam to kind of get us some practice. No other announcements other than that. Any other questions?
So the answer to that was 4?
The answer to this question here, unpaired electrons, 4, right?
Okay.
But over here, what is it?
5.
5.
Okay.
5.
Sorry, thank you.
Yeah. All right. Any other questions about anything?
Are these
I have a question. Sorry.
recorded?
Okay, go for it.
Go ahead, Camille.
Are these recorded so we can watch these lectures again?
I've had trouble I recorded the first one we did, but the other two gave me trouble. This one looks like it worked again, so I figured out what the problem was, and this one is recorded. And I'm putting them amongst all the other lecture videos that are on there's a link to it on the home page, right?
Yeah.
So yeah, this one will be available. The first one was, the second one, did we do 3? Is this the third one? Yeah, the second one isn't, but the third one here will be available.
Do you know when chapter 8 exam would be?
As soon as we finish, we'll have it open probably for a week. So I think that we'll probably have 2 more classes on chapter 8.
Is it gonna be the ACS style, or will you be making it?
It's going to be similar, hopefully similar type of questions. We're going to have to make our own questions, and we're probably going to have it delivered in the same format that the quizzes are delivered. So yeah, we're working on how the best way to proctor that is, but I think that's the only question left, is how we're going to proctor it, and I think I've identified a way, but I'm not positive yet.
So is that how our final is going to be then too? It won't be through ACS?
Yep. Well, actually, that's not true yet. The American Chemical Society has said that they are willing to give us a special thing, that it would be an online ACS thing, and the ins and outs of how that would work are not clarified yet, so we're not sure yet on that. Let's see, who was it that had a question that didn't get to have it answered yet?
I have a question.
Oh. Go ahead, Anastasia.
You go first.
Oh, you go first. Okay. My question is, is there any significance or application that we could be about the unpaired electrons? Like, is there any other question that might approach the same answer about the unpaired electrons?
Any other questions about unpaired electrons?
Yes, like a different way to say it.
How many unpaired electrons is generally what they would be asking. The other type of thing is, which one would you expect to be more magnetic, or magnetically susceptible? All right,
okay.
And that would be the one with more unpaired electrons. They might ask a question like, when you remove this electron from this atom, it becomes more magnetic. Why? And so it would probably, or more or less magnetic, and the answer would have to do with increasing or decreasing unpaired electrons.
Okay, thank you very much.
Yeah. Let's see, who was that was looking for a question to be answered? Anastasia, right?
Yes. So is there any way where we can access the slides on Canvas?
Did I put a link up there onto, let me double check here. Let's see, section 1, home page, on the home page of Canvas, on the top, yeah, the top thing on the home page of Canvas is a PDF of chapter 8 slides.
I have one more question about, I'm submitting my lab report today, but I don't know, for like the table, do I absolutely have to have a table, or can I just...
Which one are we talking about? Which lab report?
Lab 4.
Lab 4?
Yes.
No, I mean, you don't have to have a table. I like to be able to make sure I can see that you did multiple experiments and got an average and not just a single value. So just make sure that those values are included and indicated somehow, that I can see the average, right? Does that make sense?
Yes. Okay.
Yeah.
I'll put that in there. Thank you.
Yep. So Tuesday, again, for those who are in my lab, we're going to meet tomorrow at lab time, normal lab time, which is noon. and go over what's expected for you for the rest of the semester.
For both, like recitation and lab, typically, like we're all just going to be in here?
We'll actually all meet at noon. Right, we'll
Okay.
all meet at noon. Good question.
Thank
I should make sure I give an announcement about that. All right. Looks like everybody's taking off. See you guys.